Okay, so this will be section 4.2, which will be essentially just two examples on how to work with this bending stress equation of sigma equals negative MC over I, right? So let's just say this right here. We'll say recall from the last section, right, that sigma equals negative MC over I. Okay, so that's the equation we're working with. It's the bending stress equation. Much like the axial stress equation, when we're loading something along the longitudinal axis, right? The stress was sigma equals P over A. Now, instead of loading along the longitudinal axis, we're loading perpendicular to the longitudinal axis, which means we're flexing it, we're bending it. So instead of sigma equals P over A, sigma now equals MC over I, right? So that's the difference between axial stress and bending stress. It's how the member itself is loaded. So we're talking about bending now. We're talking about beams, right? Beams bend. And we're going to start calculating actual bending stress of beams. So I've put together just a quick little procedure for you guys to kind of know, like it is very procedural, right? It's step 1, step 2, step 3, and then we're done, okay? So for first step, we're going to find our reactions as always. The second step is we're going to figure out what that internal moment is for our point of interest, right? And we can either do that two ways. The first way is to draw your shear moment diagrams so that you can get the internal moment from the moment diagram. Or if you're looking for a particular point, you can make a cut at that point and figure out what that internal moment is at that point just by cutting a free body diagram and summing moments about the cut, right? Step 3, once you have your reactions and your moments, you need to figure out what the moment of inertia is. So you'll have to do that by finding the centroid and then finding the moment of inertia, because we're worried about the centroidal moment of inertia as always. And then once you have the internal moment and you've got the moment of inertia and you've got the centroid, you just put all this together into this MC over I equation and calculate what the stress is. So calculating bending stress is really no more than doing 3 different statics things and then just putting it together in one equation, right? There's really no mechanics of materials in calculating bending stress because everything just stems from our statics knowledge. MC over I, we find all of this just from the stuff that we've done in statics, okay? I also want to make out this little helpful tip right here, okay? So sigma equals negative MC over I, and in the equation, obviously we have a negative sign. We also have our next variable, which is M. M could be positive or negative, right? We can have positive and negative moments, right? When we draw on our moment diagram, sometimes the moment diagram is positive, sometimes the moment diagram is negative. So it could be positive or negative. C, the distance from the neutral axis, can also be positive or negative. We assume if it's above the neutral axis that it's positive, and if it's below the neutral axis that it's negative, okay? That was in the derivation equations for the equation sigma equals MC over I. So basically what I'm trying to make this point is we've got a negative sign, and we've got 2 other variables that could also be negative. It is very easy a lot of times to get tripped up on what your signs are. But I just wanted to make this point to you, instead of trying to keep all your positive and negative signs straight, because all they're going to indicate to you is whether it's a tensile stress or a compressive stress. That's all the positive and negative means. Is it's either if it's positive it's tensile, if it's negative it's compression. Instead of trying to keep all your mathematical signs correct on your equations, just remember that if the beam is smiley face bending, if the beam is bending up, or concave up, to where it's just bending like a smiley face, your compression on the top and your tension on the bottom, right? And if the beam is frowny face bending, your compression on the bottom and tension on the top. And what those things have to do with the moment is that where the moment is positive, that is smiley face bending. So the moment is positive, we got beam and compression, top and compression, bottom and tension. And then conversely, if the moment is negative at this location on the beam is actually frowny face bending. Okay, so just remember that. That's the way I always kind of do it, is just I'll take a look at the moment diagram, the locations on the moment diagram where the moment is positive, that beam is a smiley face bending, and the location where the moment diagram is negative, the beam is frowny face bending. We're going to get more into that later on in one of the later sections when we're talking about deflections of these flexural members, right? Calculating up the actual deflections of these beams. But just for now, just remember, if the moment's positive, it's smiley face bending. If the moment's negative, it's frowny face bending. And then you can know which side of the beam should be in tension or compression based on how it's bending. All right. So now that we've got all this kind of procedural and helpful tips out of the way, let's do our first real quick example. This is just basic example. If we've got a 2x4 wooden beam, our actual dimensions of a 2x4 are 1.5 inches by 3.5 inches. It's got a maximum moment, right, of negative 17 kip feet. Let's determine the maximum bending stress in this beam. All right, so first off, let's just draw our little 2x4 beam. All right, it's 1.5 inches wide. It's 3.5 inches tall. Neutral axis is going to be right in the middle, right? So we need M, C, and I to calculate the bending stress, right? So stress is equal to negative MC over I. We need to figure out what M, C, and I are. Luckily, most of these variables have been given to us in this equation. Our moment was given at negative 17 kip feet, correct? C is the distance from the neutral axis to either the top or the bottom of the beam. Now for this particular problem, our beam is symmetric about the neutral axis, right? So C, the distance from the neutral axis to either the top or the bottom, no matter which way you're going, is 1.75 inches, right? Just half of the 3.5. All right, I'm going to put plus or minus there because it does matter whether we're going to be in tension or compression, right? Because we're negative bending, or we are negative moment, which means we're frowny face bending, meaning the bottom is going to be in compression and the top of this beam will be in tension since we've got negative moment. But since C is 1.75 both ways, up and down, our maximum bending stress is going to be the same, right? We're going to have a compressive stress of whatever and a tensile stress of whatever. They're going to be the same value on the top and on the bottom, right? Finally, we've got to figure out the moment of inertia of this beam. It's rectangular, right? BH cubed over 12. So 1.5 times 3.5 cubed over 12. 5.36 inches to the fourth, right? This is a very basic example. Pretty much everything was given to you. At this point, now all we have to do is plug and chug, okay? So sigma equals negative M. M was negative 17 kip feet, right? Got to make sure our units all line up. So instead of converting all of the other variables to feet, I'm going to convert this 17 kip feet to 17 kip inches. To do that, we just multiply by 12, right? 12 inches per foot. So that'll cancel out my feet and I get kip inches there. So that's the moment. We multiply by C now, which is plus or minus 1.75 inches. And then finally, we just divide the whole thing by our moment of inertia of 5.36 inches to the fourth. And what we find then is that our sigma is going to be equal to either plus or minus 66.61 KSI. all right, kips per square inch, plus or minus 66.61 KSI. Plus or minus means tension or compression. We're going to have compression on the bottom because it's negative moment, tension on the top. So right here at the bottom of the beam, we've got a 66.61 KSI compressive stress. At the top, we've got 66.61 KSI tensile stress. Neutral axis, what's the stress at the neutral axis? If you said 0, you were correct, right? The neutral axis is the point where there is no strain or stress, right? So that's the basic example. We take some sort of moment, we take an internal moment that we know for the beam, we calculate moment of inertia, we figure up what C is based on where the centroid of the shape is, plug and chug into the MC over I equation. That's it. So now that we've got the basic example out of the way, we're going to work a much more comprehensive example now. And you may want to pause the video for the next little bit to get all this stuff written down. I've already kind of pre-filled out these notes a lot because everything that I've pre-filled out is the statics portion of this problem, and I don't want to waste everybody's time over fall break watching these videos just doing the statics portion, right? If you are not comfortable taking this beam that I've given you, right, we have a downward triangular load at the left side with the concentrated 15 kip load, and then there's an upwards triangular load. There's the pin support at B, so this is a prop cantilever beam. We've got a uniform load out on the cantilever portion, and we also have this concentrated moment out here 7 foot from the end of the beam. If you guys are not comfortable, I'm assuming you should be at this point. It's kind of this is the whole reason why we have a very in-depth statics review at the beginning of the semester. I am assuming at this point in this course that you're able to take this beam and find the reactions and draw the shear moment diagrams for this particular beam. All right. We also have the profile of this beam. It is a non-symmetric I-shaped beam. So the top flange of the beam is 10 inches by ½ inches. The bottom flange is 7 inches by 0.35 inches. And then we've got a 33 by 0.35 inch web for this I-beam. Okay. Since it's not symmetric, right, we don't know where the centroid is located vertically, right, Y bar. We're going to have to calculate Y bar, and then once we have Y bar, we'll be able to calculate the moment of inertia I. So again, this is just the statics portion of the stuff. We reviewed all of this at the very beginning of the semester. I'm going to assume that you guys know how to calculate centroids and moment of inertias. If you're looking at this saying that you don't know how to do this at this point in the semester, you need to sit down and figure this out. Okay? So let's just look at what the problem says. I've given you all the static stuff. I've found the reactions. I've given you where the centroid is. I've given you the moment of inertia. And I've given you the shear and moment diagrams. All right, I challenge you, if you're not sure where all these numbers are coming from, sit down and figure this out on your own. Okay? So the problem statement for this beam says the maximum allowable tensile and compressive bending stresses for the beam shown are 32 KSI and 19 KSI, right? 32 KSI is the tension stress, is the allowable tension stress. 19 KSI is the allowable compressive stress, all right? This would be very, very typical values for a steel beam. If the question is, can the beam safely carry the loads? All right, I've given you an allowable stress. Let's calculate the actual stress and compare them to the allowable stresses. If we're below the allowable stresses, we're good. If our actual stress exceeds the allowable stress, the beam has failed. All right. Second question that this example wants to know is, what is the stress at point D at a location that is 5 feet to the left of support B? All right, point D is over here on the cross section. It's 4 inches above the bottom flange. All right, I've located point D 4 inches above the bottom flange, meaning that it is not at the centroid and it is not at the top or bottom of the beam. So we're going to have to figure out what a stress is at some other point other than the maximum or minimum values. And we'll also have to figure out what this moment is 5 feet to the left of support B. So we'll do that too. Actually, we'll just give you that portion of it because it's just statics. But let's just take a look at this, all right? So we need to calculate the actual stresses. Let's do it. Let's take a look at this. So sigma equals negative MC over I. Like we just said, the moment and the C variable, the distance from the neutral axis, both of those variables could be negative, right? So taking a look at our moment diagram, the very beginning portion of our moment diagram is positive, whereas the rest of the moment diagram is below the zero, right? It's negative, right? So we've only got a small portion of this beam in positive moment, and the majority of this beam is in negative moment. So the very first beginning is smiley face bending, and then the rest of this beam is negative bending, which is frowny face bending. So this all matters because the way in which the beam bends tells us whether the top of the beam is in tension or compression, right? Same thing with the bottom. Depending on how this beam is bending, the bottom can be either in tension or compression. And you'll notice too that it'll make a difference for our C variable because our shape is not symmetric, right? Our neutral axis, based on the calculations that were given to you here, our neutral axis, or the centroid, is 19.11 inches from the bottom, or it's 14.74 inches from the top, right? That's a total, the beam has a total height of 33.85 inches, right? So that the location of the centroid is 19.11 from the bottom, or you could look at it as being 14.74 from the top, right? So if C in our equation is the distance from the centroid or the neutral axis to either the top or the bottom, our C value is either going to be 19 or 14, right? So it's going to change depending on whether we're looking at the points above the neutral axis or the points below the neutral axis. What this basically tells us is, looking at our sigma bending stress equation, is since moment can be positive or negative and C can be two different values, one of them positive, one of them negative, what we end up with is 4 different possible variations for what sigma can be. All right, we're going to have a positive and a negative moment and a positive and a negative C. We need to investigate all the possible values that sigma could be. Main thing that we have to look at is what is the stress at the location of the maximum positive moment, 3.03, and what is the stress at the location of the maximum negative moment, negative 371. All right. So let's just say this, right? So the step 1 here, max stresses. All right. So part A, positive moment. At the location where the maximum positive moment is this 3.03 kip feet, right? It's a small moment, but it is positive. It is the maximum positive value that we have. So where we have positive moment, let's find sigma at the top of the beam, okay? We got positive moment, top of the beam, it's smiley face bending, top of our beam should be in compression, right? So that's what we can think of. So let's plug our values in. Sigma equals negative MC over I. We have negative. The moment is 3.03 kip feet. We're going to convert that to kip inches so that we can keep it all straight. we need to have our C value, right? So we're looking at the top of the beam. The point that we're looking at is at the very top of the beam. So we need the distance from the neutral axis to the top of the beam, which we've already said was 14.74. All right, so C becomes 14.74 inches. So that's negative MC over I, which we said I was 3,035 inches to the fourth. At this point, we just plug and chug, right? So we've got all the variables in there. We've only got one negative sign in this equation, so it comes out negative, which means compression, which is what we would assume it would be, so we know we're right. This comes out to be 0.177 KSI, right? It's negative, which means compression. And that's the stress at the top of the beam at our location of maximum positive moment. So what was the allowable compressive stress? The allowable compressive stress was 19 KSI. So if we've got a stress of 19 KSI, an allowable stress of 19 KSI, and we've got an actual stress of 0.177 KSI, we are okay at this point. Okay, that stress is low. We're good. It's not going to fail the stress. All right. So now let's look. We still need to look at the location of maximum positive moment. Let's look at the stress at the bottom of the beam, though. So sigma at the bottom, because the bottom of the beam will be in tension. Top of the beam we just calculated to be in compression. Bottom of it's going to be in tension. We need to figure out what that tensile stress is at this location of positive moment and see if it exceeds the allowable. So negative MC over I, so we're still negative. The moment is still 3.03. Again, multiplied by 12 for a unit conversion. C this time is the distance from the neutral axis to the bottom of the beam, because that's where we're looking at, which we said was 19.11 inches from the neutral axis to the bottom. But this time, since our distance is going below the neutral axis, this C value becomes negative, so we get minus 19.11. Again, divide by the 3,035 moment of inertia. Inertia doesn't change, right? Inertia is inertia. We ratio this up, we get 0.229 positive KSI, right? This will be tension because it's positive. And the allowable tensile stress was 32 KSI, correct? So that means, again, we're okay here. That stress is very low compared to the allowable. So we're good at the location of positive moment. The next thing that we need to do is investigate our stresses on the beam at the location of maximum negative moment, this negative 371 kip feet. So it's the same procedure. We're going to investigate top and bottom stresses, but over here at this location where the maximum value is negative 371. So this will be part B, right, where we have our maximum negative moment. Again, investigating stresses at the top and bottom because they're different. They're not symmetric, right? Y bar is not in the middle. So sigma top is equal to negative MC over I. M this time is negative 371. Multiplied by 12 for that unit conversion. And our C value, we're looking at the top, right? So from the neutral axis to the top was that 14.74 inches. And again, we divide by the inertia, which was 3,035. So all of this comes out in kips and inches, so it's KSI, and it's going to be a positive value, right? And it comes out to be 21.62 KSI, right? This is tension. It's positive. The two negatives cancel out, so it comes out positive, tells us in tension. So 21.62 KSI actual stress. Allowable is 32 KSI. Tells us that we're below the allowable. means we're good. Okay? We're okay. Lastly, let's look at the stress at the bottom of the beam at our location of maximum negative moment. The equation again is negative MC over I. So negative 371 multiplied by 12 for that unit conversion. But this time our C value, our C variable, is the distance from the neutral axis to the bottom of the beam, which was that 19.11 inches. But it is negative this time because we're below the neutral axis. So negative 19.11, again, divide by that same moment of inertia, 3035. Plug and chug on these variables, what we get is a negative 28.03 KSI, right? Came out negative. This just tells us compression. So if I've got a negative 28 KSI in compression, my allowable compressive stress was only 19 KSI, right? So actual stress 28, allowable 19. We are overstressed on this beam, right? This is no good. This beam will fail. This beam will fail on the bottom flange. The bottom flange is 7 by 0.35 inch bottom flange is not big enough to handle this negative 371 kip feet maximum negative moment. So for us to get this stress down, we need more inertia, which the best way to do that, we can either make this beam taller or we can make that 7 by 0.35 inch flange bigger, maybe make it like a 10 inch by 0.35 inch flange and get that inertia bigger that way as well. All right, but we have overstressed this beam. So to answer the question that the problem asked is this beam safe to carry the loads? The answer is no, it's not. All right. So finally, we need to the last part of this example was what is the stress at point D, which is shown on the cross section, is 4 inches above the bottom flange, at a location that is 5 feet to the left of support B, right? So instead of just figuring out what the maximum stresses are, because the maximum stresses occur where the maximum moments are, now I'm asking for what is the stress at a specific point. Okay, so 5 foot to the left of point B, and at this specific point on the cross section, which is not going to be the maximum values, we need to calculate this up. All right, so let's take a look at this. Let's go to our moment diagram. Right, 5 foot to the left of point D is somewhere here. Five foot to the left of point D. This moment actually comes out to be negative 362.8 kip feet. Okay. Again, that part is statics. You're going to have to do your integrals for the load shear moment relationships. Figure out what those values are. Plug in a number. You'll get negative 362.8. Again, you need to be comfortable calculating these types of equations, being able to figure out what your moments are. So if you need practice on this, please practice with this example. Prove to yourself that the numbers I've got here are correct. All right, so we've got the moment at 5 foot to the left of support B is negative 362.8. So we've got that. The inertia doesn't change. The only thing else we need to look at is points, is the C variable. So this will be part, I guess, 2, right? Part 1 was the maximum stresses. Part 2 is stress at point D. Stress at D at 5 foot left of B, right? Because moment depends on where you are lengthwise of the beam, and the C variable depends where you are on the cross section relative to the neutral axis, right? So we've got to calculate both of these. So sigma equals negative MC over I. Moment was negative 362.8 kip feet. We can figure that out. We figured that out from our moment diagram and our equations. Inertia still 3,035 inches to the fourth. But this time C really is not C value, right? We're not really looking at C. We really need to put Y here to be absolutely technically correct instead of C, because C is technically the distance from the neutral axis to the top or the bottom, right? What is the maximum values that Y could be, top or bottom, right? So this time we're really, to be 100% technically right, we need to put Y here. So Y is the distance from the neutral axis to our point of interest, okay? On the cross section, our point of interest is point D, which is 4 inches above this bottom flange, okay? We know that Y bar, the location of the centroid, is 19.11 from the bottom. So if we took 19.11 minus 0.35 minus 4, that'll give us what our new Y value should be in our equation here. So we'll have this 19.11 minus 0.35 minus 4. And then the only thing about all of this is that it needs to be negative because we're below the neutral axis. What this comes out to be is 14.76 inches. And it's negative once again because we're below the neutral axis. We're looking at a point that is below the centroid. That's the only reason it's negative. So now that we've got this, we calculate sigma. So sigma equals negative m, which is negative 362.8 kip feet, right? Kip feet got to get converted to kip inches, so multiply by 12. Y is negative 14.76 inches. C, 3,035 inches to the fourth. Sigma at this point along the beam and on the cross section, our stress comes out to be negative 21.17 KSI, right? Negative means compression. And again, so it was just asking what the stress was, so that's okay. We just calculated the stress, 21.17 KSI, and compression. Again, looking at this point is actually failing as well because our allowable compressive stress was only 19 KSI, right? So just looking at it again, this point is also no good, right? This beam has failed in negative moment. That bottom flange of the bottom flange of the beam has failed in negative moment. All right. So this is about as hard as it can get, guys. This is calculating bending stresses. So just reviewing this problem, right? You get some type of beam. Step 1, you got to find reactions. That's statics. Step 2, you got to figure out where the centroid is and what the moment of inertia is. Again, that's statics. Step 3, draw the shear moment diagrams. Again, this is statics. Once you have all of this done, you just start combining all of these variables together. So you got the moment from the shear moment diagram. You get C value from where the centroid is. You get I from the moment of inertia. You just combine all of these different statics procedures into one equation and we get stress. All right. That's all this is. Bending stress is nothing more than just combining a bunch of different statics things together. All right. So you guys work on this problem. If you need to verify these numbers, the shear moment diagrams, the centroid, moment of inertia, reactions, all, feel free to check yourself, go through this beam, calculate these reactions yourself, calculate the centroid, moment of inertia, calculate all this for yourself, verify it, prove it to yourself that it's right. And then I think I gave out a homework that the homework had another 1 or 2 bending stress problems on it. So that homework should be posted to iLearn. You guys should go out there and look at that homework. and watch these videos, be able to do the homeworks. If you have questions, as always, either text or email them in. And we will see you guys on Thursday the 13th, because the 11th will still be fall break. All right, guys, have a good break. We'll see you on Thursday.